Welcome to MRP classes. It is a continuation of energy of electrons in power model atoms. Here, let me introduce you some simple and important numericals based on energy equations of electron in power model. Let us see the first question. The ionization energy of hydrogen atom is 13.6 electron volt. Please remember this value. 13.6 is the even value of hydrogen atom. What will be the ionization energy of helium plus and lithium 2 plus side? Here helium plus and lithium 2 plus are hydrogen like atoms. Therefore, I said to you in the previous lecture, ionization energy is equal to negative or positive value of energy of electron. In the case of energy of electron, I have introduced you an equation. The equation was this. En is equal to E minus EH ground state Z square by N square. You get this value, make it a positive value, you will get the ionization energy. Because ionization energy of an electron of initial is equal to positive of En. En in terms of hydrogen is En is equal to minus EH ground state Z square by N square. En EH ground state, energy of hydrogen in ground state into Z square by N square. If you get this value, make it positive, you will get the ionization energy. See, ionization energy is equal to minus of En, that is net is positive, it's a positive value. E helium plus is equal to, if you have given hydrogen, then make the equation like the hydrogen ground state into Z square by N square. What is hydrogen ground state value? I have given you this value again. E1 of hydrogen atoms minus 13.6. Therefore, this value is hydrogen atom minus 13.6 into Z square for N is equal to E plus helium plus N is equal to 1. Therefore, my energy of helium is minus 54.4 electron volt. Therefore, ionization energy is positive value. Okay. Next is E lithium 2 plus minus 13.6 into Z square by N square. Z square by N square, that is 9 by 1 minus 122.4 electron volt. Its positive value is the ionization energy. Okay. Now let us go to the next question. This is the second question. Please see this question. Okay. The electron energy in hydrogen atom is given by En minus 2.18 into 10 raised minus 18 joule by N square. Calculate energy required to remove an electron from N is equal to 2 orbit. What is the longest wavelength of light that can be used to cause this transition? Energy of hydrogen atom is given by En is equal to minus 2.18 into 10 raised minus 18 joule by N square. Calculate the energy required to remove an electron from N is equal to 2 orbit. What is the longest wavelength of light that can be used to cause this transition? Calculate the energy required to remove an electron from N is equal to 2. That is the wanted ionization energy from N is equal to 2. How much energy required to remove an electron from second shell? Therefore, here you calculate what is the energy of electron at second shell, second orbit. Make it positive, that is ionization energy. Therefore, please calculate E2. En is equal to E2 minus 2.8 into 10 raised minus 18.4. You get this value in negative, make it in a positive, multiply with the negative side. Okay. Yeah, finally you will get this much joule. Therefore, this is the ionization. Simple, very simple. You are just calculating, you are just putting N is equal to 2, that is 4. You will get En, make it positive, that is ionization energy. Now the second part of the question is, what is the longest wavelength of light that can be used to cause this transition? Therefore, this transition, you are removing an electron from second shell, is possible when you give an energy of photon hc by lambda. You can this is the energy of electron in the second shell. The energy required to remove that electron or photon, energy of photon that can be used to remove that electron is hc by lambda. Put the value of hNc, then calculate the lambda. Lambda is this. I hope this question is solved. Now I go to the third question. Very interesting question. The bond energy of H2 is 436 kilojoule per mole. Calculate the minimum and frequency of photon to break this bond. Once again, the bond energy of H2 is 436 kilojoule per mole. Calculate the minimum frequency of photon to break this bond. Therefore, this is the principle. You have given HH photon, you give the photon, it breaks, you are getting to it. How much energy? What is this? Therefore, here please calculate hc by lambda. But you are given bond energy. But very careful, bond energy is given per mole, but here only one molecule. Therefore, you have to calculate what is the energy per molecule. This is possible when you divide this with 6.022 into 10⁻23. Why I divided? Because it is for 1 mole. Therefore, 1 molecule you have divided with 6.022 into 10⁻23 joule. Therefore, very careful, this is the energy required to break one bond. That is the energy of photon, h nu. Therefore, the frequency is equal to nu is equal to divided by Planck's constant. The value, this is the Planck's constant value. The final answer is this. Okay. Therefore, this is for energy to break one bond, that is equal to the photon which fall on that bond to break. Therefore, the photon energy is h nu. Therefore, frequency is this. Okay. Next question. How much will be the kinetic energy and total energy change? Kinetic energy and total energy change of an electron in hydrogen atom if the atom emits a photon of wavelength 4860 angstrom. How much will be the kinetic energy and total energy change of an electron in hydrogen atom if it emits a photon of wavelength 4860 angstrom? An atom emits a photon, then how much will be the total energy change? How much will be the kinetic energy? We know one relation. Total energy is equal to half of the kinetic energy, or kinetic energy is equal to positive of the total energy value. Okay. Therefore, we can calculate total energy change first. Total energy change when an atom emits a photon of wavelength 480 is equal to, that is total energy change delta E is equal to hc by lambda. hc by lambda. Because if an atom emits a photon of wavelength, this is the total energy change. Therefore, you will get the total energy. Please put the lambda value here. You will get the value. This is the total energy. This is the total energy of loss. Then, yes, total energy loss. Therefore, kinetic energy is equal to loss in energy due to release. That is, this is the kinetic energy. Here we have calculated delta E. That is why there is no negative sign. This loss in total energy has been converted into kinetic energy of the electron. When an electron falls down, when an atom emits a photon, okay, total energy change. When an electron emits a photon, when atom emits a photon, electron energy comes down. Therefore, total energy lost will be used as the kinetic energy of the electron. Now, one more question, last question. Yes, very interesting question. Please take. Hydrogen atom is exposed to the radiation of 102.8 nanometer and gives out induced radiations. Find out the lambda of induced radiations. Hydrogen atom is exposed, and hydrogen atom is exposed to a radiation of 102.8 nanometer and gives out induced radiation. Find out the wavelength of induced radiations. The induced radiation means your hydrogen atom in the ground state, when it is exposed to light, it is excited state. After the excited state, it comes down to ground state. H nu dash is emitted. This radiation is called induced radiation. They wanted to know what is the wavelength of this radiation. Therefore, it is emission radiations. Therefore, this delta E is equal to H nu dash. Please remember, delta E is equal to H nu dash. Therefore, after excitation, it will go to the de-excitation. During the de-excitation, energy level changes. During that, it emits the photon. We wanted to calculate what is the wavelength of induced radiation. Therefore, your atom has been exposed to this much wavelength. Therefore, first we can calculate energy corresponding to this wavelength. The energy corresponding to this wavelength is Hc by lambda. Here I use very important. Please remember, if H is taken in electron volt, C taken in nanometer, you will get 1242 electron volt dBm. Please by heart this. If H is taken in electron volt, normally H is taken in joule per second. If you take in electron volt and C in nanometer, you will get 1242 electron volt nanometer. Therefore, this also nanometer, you will get this much electron volt, 12.42 electron volt. Now, we know that ground state energy level of hydrogen atom is 13.6. I have told you in the previous lecture. First excited level energy in electron volt is 3.4 electron volt. Second excited level, n is equal to 3, 1.5 electron volt. This is the energy in energy when at n is equal to 3. This is energy at n is equal to 2. This is energy at n is equal to 1. Now, there are three possibilities. One is, it has been coming down from 2 to 1, 3 to 1, 3 to 2. When it comes to N2 to N1, the wavelength is lambda 1, the photon wavelength is lambda 1. When it comes from N3 to N1, a photon is emitted with a wavelength lambda 2. When it comes from N3 to N2 level, a photon is emitted, its wavelength is lambda 3. We can calculate each wavelength. When it comes for lambda 1, see, this is the energy difference when n is equal to 1 to n is equal to 2. What is energy? Because this is the first level energy, ground level energy, the second level energy, the energy difference is 10.2 electron volt. Therefore, lambda is, which is equal to Hc by lambda. Therefore, lambda 1 is equal to Hc divided by this value, 10.2 electron volt. Hc, I have told you the Hc is equal to 1242 electron volt nanometer. 1242 electron volt nanometer. Therefore, I divided 1242 electron volt nanometer divided by 10.2 electron volt. Therefore, I got this much nanometer. This is lambda 1. Now, what is lambda 2? Lambda 2 is equal to your atom is emitting when it comes from N3 to N1. Therefore, the energy difference between N1 and N3 is, N1 is this, N3 is this, the energy difference is this, 12.0. This is the delta E. Delta E is equal to Hc by lambda 2. Therefore, lambda 2 is calculated by Hc by delta E. Delta E is this. Hc is 1242 electron volt nanometer divided by 12.08 electron volt. When you divide, you will get 102.8 nanometer. Now, the third is lambda 3 is, that is, it comes from N3 to N2. The difference, N2 minus N3. What is the difference? 1.9 electron volt. The difference is 1.9 electron volt. This is the delta E. This delta E is equal to Hc by lambda 3. Please calculate the lambda 3. Please remember, Hc have a value in electron volt 1242 electron volt to nanometer. Please by heart this 1242 electron volt to nanometer. By heart this divided by 1.9 electron volt, you will get 653.6 nanometer. Therefore, the question is, hydrogen atom is exposed to the radiation of 102.8 nanometer and gives out induced radiations. Find out the wavelength of induced radiations. Therefore, these are the possible induced radiations. Thank you for watching. Please subscribe my channel.